Welcome to another coding session. Now with improved sound, I hope. I got a new mic, so we should have some better audio quality this time, which I'm very happy about. I think the audio quality up till now has been pretty poor. So hopefully, hopefully we've got some improvement there. I'm just going to do a bit of a quick recap of where we're at. We're creating a language, a low-level, quite explicit language. The motivation being that the more directly it translates to assembly, the easier it will be to create a compiler. So yeah, it's a compiled language. And the kind of lofty end goal is that we would like to compile parts of the program to GPU assembly. And so we just write code in our language, and then we can choose which part of it gets run on the CPU, which part of it gets run on the GPU. That's kind of the end goal, but at the moment we're just doing very basic stuff. The program grammar is like this. We have a few productions. So we start with a program, which is one or more statements, which is why we have the star. Each statement could be a scope, an assignment. I've just realized that we're missing one here because we added a new syntax for declaration. So that's the declaration syntax. This is assignment. We can do an exit call. And if we come across a scope, that's just, again, one or more statements that are within curly braces. And a term, which is used in these few places, can either be an identifier or an integer literal. And this is what our code looks like. So very simple so far, and it can't really actually do anything useful. So that's what I want to do this episode. We want to actually do something useful. And the useful thing that we want to do is arithmetic. So I think what we're going to need to do is introduce a new production here. So let me make space for that and fix all the indentation because it messes it up. I think just something like that. And we will need a new line somewhere, it looks like, I guess at the end. There we go. So now this one is going to be an expression. And the expression can be either, it could be just a term. That's the most basic case, is that it's just a term. But it could also be some arithmetic. I did mention I'm adding arithmetic, right? I said we wanted to actually do something useful, and the useful thing is arithmetic. I'm not sure if I actually said that. So that's where we have like term plus term, term minus term, term multiplied by another term, and term divided by another term. I'm not sure why these spaces are not showing up, but this whole syntax for writing grammar, I'm very new to. I don't really know how it works, so that's good enough for now. We're not going to have, chaining of arithmetic operators yet. I don't know if chaining is the right word, but, we're going to say, we are going to allow something like y plus 3. Let's go result. But we're not going to say y plus 3 minus 7. That's not possible. We're not going to chain together. If we did do that, and we had to multiply, for example, then we need to do this first, and then this. Well, and then y plus the result of this. So that's a little bit of extra complexity that we'll get to maybe in the next episode, actually. But I think for now, we're just going to stick with a single binary operator in our arithmetic. So this is all we can do right now. And then we're actually going to use the expression, right? So anywhere where we had a term before, now we can have an expression. right? So we can declare using an expression, which is what we've done here. We can assign an expression to an identifier, or we can embed an expression directly in the exit call. Nice. So how do we go about implementing this? Let's go through the usual stages. Tokenization, we have 4 new tokens. They're all just single character tokens, so it should be nice and easy. So we have plus, minus, asterisk, and backslash. It's not forward slash, is it? I always get these confused. I feel like it's backslash. So when it comes to tokens, we're literally just saying what the token contains. So in this case, like an asterisk, in the context of mathematics, that's going to be multiplication. But I don't know what we're going to use, but in some languages, dereferencing a pointer is an asterisk. So that's the same token, different context, very different meaning. So for tokens, we just say it's an asterisk. We don't know what it, semantically, we don't know what it means yet. We just know it's an asterisk. So we have 4 more of these token cases. I feel like there's probably a more concise way to do this than having all these cases like this, but anyway, we'll go plus, minus, asterisk, and is it backslash for division. Great. That's easy. Now we go to our parsing, where we move through our tokens, and depending what we find, we generate different nodes in our AST, which is an abstract syntax tree. I should really visualize this tree somewhere. I never really visualized it. I mean, if we go into here, we pick a spot, then the kind of thing we're talking about with this AST tree is the tree doesn't actually have a root. It starts at the top with, like, say there's multiple statements. And this first statement could be, say, an assignment statement. An assignment statement. So actually, I think then what we call it in our node types, we say what sort of statement it is. So this would be assignment statement. And the children of the assignment statement, like this, I think that's going to join. Yeah, very nice. Will be the, I just call it like the left-hand side node, which actually will be an identifier, because you're always assigning to an identifier. So I'll put in brackets left-hand side, but it's like the left-hand side of the assignment is the first node. Then the second node is going to be an identifier slash a integer literal. And that's the right-hand side. And then you have more statements that would have, depending on what sort of statement it is, they have different kind of children nodes. That's about it. I guess we can have a scope, which will then again have more statements as children. So this is the tree, and you can sort of say that this is the program. You know, it's like the root. Now, technically, I don't actually make a program node, but just for visualization, this is kind of what we have with this is like what the AST looks like. We'll have to do shift, something like this. And this statement could be, just to sort of finish it off, we could say this is an exit statement, and the exit statement also just has, the only thing that it has is something that says what we're exiting with, which could be an identifier, an integer literal. Now that I visualize this, we're actually going to change it. But it's nice to have it visualized. This is what, when I say AST tree, this is what we're talking about. Something like this, where we take the stream of tokens, the raw stream of tokens, and we turn it into a nice tree that represents our program. That's the parsing step. So what we're going to do now is, maybe I'll do it. We'll put it in the exit statement, or yeah, we'll put it in the exit statement. So maybe we will do something here. We'll put this here, and we'll say that this is an expression. So we'll call it an add node. And that could have a left and a right node under it. Right? So this kind of concept here is what we are adding. The concept of having, like, you know, within the exit statement, we could have an addition of 2 values, and the result is what the exit statement wants to use. So I think that's nice to have that visualized. So now, I don't think this is actually used. I think we took this out, didn't we? It is used here, but we set to identify our integer literal further down. It's not, you know, it's not actually used. So let's put it here between these and the identifier. I feel like that's a nice place. Add, subtract, multiply. See, so these, the nodes are more semantic. They have more meaning in the context of the program, whereas the tokens are very raw, just like, hey, I found this in the file. I don't know what it is, but I found it. Like, I don't know what it means, but this is it. Divivid, divide, like that. And we're going to need, after our statement declarations, we have a parse term. We're going to put a parse expression, like so. And so if we go back to our grammar, we need to handle these 5 cases. Okay. So the first case is, well, I guess we need to get our LHS node, right? Would be the result of parsing a term. We're declaring that. So first thing we need to do is parse a term. I think we have to have an empty return. And is this still correct? Yeah, I feel like this is still correct. This is still parsing a term. That's totally fine. First thing we need to do is parse a term, and then we're going to have ourselves a partial switch, which looks at the next term, the next token, but does not consume it, and says, hey, what type is that token? Because If it is a plus, then I want to create an, then the type of this node, no, the token type won't be a plus. No, it will be a plus. Sorry. I'm thinking, because for some of these cases, they're going to be different names, but we go plus, minus, asterisk, because we're still talking about the nodes, and backslash. That means that our node is line number, column number. I need to do that, don't I? And something I kind of realized is that I'm doing this for some of our nodes, but not all of them. You know, like we create this param node here. Well, actually, that's the result of parse term, so it probably is getting the line number, column number. I think there are some nodes, though, that we create without doing this. Is that true, or is it not true? Yeah, like this one, this left-hand side node. We'll give it a type and a value, and that's it. Yeah, maybe at some point we should go through and make sure they all have that metadata, because that would be helpful for our error messages. So if we have a plus, that means our node type is an add, right? If we have a minus, then we are subtracting. If we have an asterisk, we are multiplying. And if we have a backslash, we are dividing. Cool. And then we get a right-hand side node, and we do that by parsing another term. The part that I've missed is that we actually need to append to the children of this the expression node. So we should go node.type equals. We didn't create that. We didn't create that. We need an expression. Oh no, sorry. Because we're setting it down here to add, we've got more specific ones. Add, subtract, multiply, divide. Okay. Where were we? We're parsing our expression. We needed to actually append these nodes, left-hand side and right-hand side. We've set a type and the metadata on this one. I don't think there's anything else we need to set. We set the type. We've put children, got this metadata. We don't have a value, but there's not much. We don't need to put a value in there. Values are more for the leaf nodes, I feel like, more for like terms is where we, terms and identifiers, those kind of things. Well, identifiers are terms, I guess. So I think that's it. I do like how much easier our parsing code has gotten since we started using this, we've been using this token stream. So actually, I think we should do operator token, because we need to say next token, right? We don't want to just peek it. We need to actually consume it. So we need to do next token. And we probably can go, say it's a slice of token types and limit it. Say that it's got to be one of these. So if you find an expression, what I haven't done is, okay, it is valid to not have one of these as the next token. That is valid because if one of those is not the next token, then we're just going to assume that our expression is just a term. If we don't find one of these after the term, we just assume this was the expression, just this. And then say the expression was part of an exit statement. It's part of the exit statement's parser's responsibility to check that the next token is the correct one. We've established it's not one of these. Maybe it's a bracket. And if it's not a bracket, well, then we throw an error. So I'm going to say operator node types equals, that. Can I do that just with a slice? Yeah, I guess so. Okay, nice. And I'm just going to do this manually. For operator node type and operator node types, if operator node type equals, so we do need to peek the token. But not consume it, because we don't know whether it's ours yet. We don't know whether it's part of the expression yet. And if we find it, we're going to have to keep track of whether we've found it yet. Here we found an operator. So here we're going to say, yes, we have found an operator. And we can break. And then after this loop, we're going to say, if we never found an operator, that means we're done, right? We filled out this node. But we didn't give it the type yet. I guess in that case, it just resolves to a term. We don't need to have a node above it. It's still like this. If we do find an operator, then we create a structure like this, where we have the operator node, the add, or I guess it's the expression node, and then we have two children. But if we don't find something like this, we just find a term, then we do something like this, where we just have the individual node. So this LHS node that we grabbed, we want to return, but before we do, we say node.type equals LHS node.type. Actually, can we just say this? That's probably the easiest, isn't it? Because these nodes are just simple objects. Copying a dynamic array should work. Not that we have any children for this node. So if we fail to find an operator, we've peeked the next token, we've checked if it was an operator. If it wasn't, then we say, okay, the LHS node is the node of the expression, and we return. Great. Otherwise, we do want to grab the token. I don't think we need to assign it because we already have it from our peek. But we might as well put this in here and verify it again. I mean, this loop has already verified it, so maybe that's a waste of energy actually. But we just grab it. No, I feel like this is a bit easier to read actually. When we come across this, we can say, okay, we're getting the next token from the stream, and it's our operator token. Actually, that should be operator token types. Yeah. Okay, so we've got the operator. We assign the correct type to our expression node, and then we grab the right-hand side. That's how you parse an expression. Okay, I'm pretty confident about that. And then wherever we had parse term, we actually do parse expression. Parse term should only be present in the expression here, I believe. Terms only show up in here. So anywhere else where we had parse term became parse expression. It is handy having that grammar there, I have to say. So any of these, so these ones, parse expression, then if we click on parse term and it shows us all the places where it was called, I can see it in the side here, these little lines. It's just twice that it's called, and it's in parse expression, which is what we expect. Great, I think that parses it. Now we go to generation. I think this is where it gets a bit more interesting. So I do want to change how this works a bit. We don't have a generate. We don't have a way to just generate a term right now. Someone did comment on one of my videos saying that it would be good to have the generate term. I'm going to do a little bit different to what he or she suggested, because what I'm going to do, generating term is basically establishing where the value is. So it's going to return, either an address on the stack or a register or a literal. If it's an integer literal, then it'll just return the literal. So then what we return here, we can just plug that straight into our function that called it. So that's pretty nice. I hope that will work nicely. So let's find somewhere where I think somewhere like this is where we are basically trying to parse a term. In this case, it's the right-hand side node of an assignment, which is a term. We're checking what it is, checking that it exists. The variable exists if it's an event identifier. I'm just going to take these off. They're not really serving any purpose. They used to be my microphone, but now that I have a dedicated microphone, I don't know why I was wearing them. So let's take this and put it in our generate term. And it's not right-hand side node, it's just node. Failed to generate term. I feel like these messages are kind of superfluous. We don't really need to have them there, but I mean, when I say that, what I mean is that normally if you're coding away and the compiler gives you an error, it doesn't give you this kind of information. This is more useful for me right now when I'm developing the compiler, because it allows me to see like, it was in the generation of the term. That's the function that I can go and look at to see what went wrong. But for a user of the compiler, it's probably not that useful. So I might just put this here so it's not expecting a return. And okay, so the difference now is going to be this here is what we're really after. This is where in the case of an identifier, this is what we want to insert into our code. Like this is where the identifier's value is stored. So let's say I'll generate term here as well, undeclared identifier, invalid node. And so instead of printing to the file, I think we don't actually need to bring the file in here because we're returning a string. So I think instead it's more like a return strings.concatenate, is it? Strings.concatenate. And then I believe it's an array of things. So the first element is going to be this RSP plus. Then we're going to have our integer, which we'll figure out later, and then a closing bracket. We can't just put var offset there, can we? Or can we? That's not yelling at me yet. Now it is. Okay. So I think that's like I to A. Not declared by OS. Okay. I'm pretty sure there is a integer to ASCII. That should give us a string. Maybe it's in strings. Okay, I think I'm going to have to search for this. So Odin I to A. Packages I to A. Strconv. Yeah, Strconv, that's a string conversion package, which we don't have yet. Strconv. Come back down here. So strconv.I to A 22. So it takes a byte array and a number. That's not quite what I was expecting. I can't just do string, can I? Strconv dot, it's not parse. So if we have a number and we want to turn it into a string, so it's the opposite. It's, no, that's, I feel like I to A is correct. Integer to ASCII. Oh, it's just calling append int on a buffer. So it's just putting it into a buffer. Okay. So let's just declare some ridiculously oversized buffer of bytes. Pass that in there along with the integer. I think that's how it worked. I think it needs to be a slice. In Odin, this is how you convert, like it could be a fixed size array or a dynamic array or probably other things as well. And then there's also a slice type, which is like a view into whatever it is. Could be, fixed size array, dynamic array. This is how you create a slice. Like it could be like, 1-4 to take a portion of it, but if you omit those numbers, then it's just the whole thing. And that conveniently returns a string. So I think we just put that there actually. Okay, that works. So in this case, we want RSP plus whatever the offset is, closing bracket, like that. And in this case, I think it's much easier. We just want to return, because this is just a literal, we just want to return the value. Okay, so now we have a way to generate a term. We also want to be able to generate an expression. And I think this is also going to return a string. So in this case, our expression could be just a term, or it could be terms with those. So let's do a partial switch again on, oh, we need to take these things in. I don't know, do we need it? Oh, we do need the stack here. We do need the stack, okay. So no dot type. And if we're looking at one of these arithmetic ones, subtract, multiply, divide, and the default case, if we don't find one of those, is that it must be just a term. So we should be able to return generate term like that. If we do find one of these, that's where we want to actually do our maths. So we do want to print to the file. So we do actually want the file for this one, because we want to print the math statements. And we want to do the maths in a way that, well, I guess the result of the math is going to be in a register, and then we will return what that register is. So that wherever the expression is, they can use that register, or maybe they will use, the stack pointer or the literal. There's a few things that could be the result of an expression. So if we're adding, here we go, here's some assembly. Then we want to do add. And a register that we're going to use. I don't think we want to use racks, because, like, for example, in this exit statement, racks is already used. So then if we say, like, this, if this gets substituted with racks as well, that's going to be bad. Well, the expression is going to overwrite the 60. It's not going to be 60 anymore if we reuse racks. So let's use rbx, I think. So first, I guess we're going to need to move something into rbx, which would be the left-hand side. Assign LHS to rbx. And the left-hand side is going to be the result of generate term. So we go generate term with node dot. Oh, let's grab the nodes out. Where do we do it? Here. I feel like that's a bit easier. And what else do we need? The stack. So we generate our term for the left-hand side. We put it into rbx. Then we do an add, which will add rbx and whatever this is, and put the result in rbx. So we add the RHS to rbx. That's kind of the idea. All right. Now I think this might be a common thing that we do. So let's take that out for now. We subtract, multiply. So that's subtract RHS from RBX. This, I have a feeling is wrong. I think it might be like IMUL. Multiply RHS by RBX. And okay, we'll put this, division is more involved. I found this much out. Do I need to, it's because I need to be returning these. Oh no, I need to return RBX, right? In this case, we will return whatever the result of the term is. And in all the other cases, we've put the result in RBX. That's the idea. Okay. I'm pretty sure this is wrong. This might be wrong too, but I'm pretty confident about these ones. So that's generating an expression. And then how do we use that expression? Well, in the exit statement, this part here is our expression, right? So it's basically we want to move into RDI the result of the expression. We need to put the file in there too, like that. I don't think we need to do any of this because I think the in here, you know, in generate term is where we do all that kind of stuff now. So that makes this a lot more concise. Hey, that's nice. I like that. So yeah, the result of the expression goes into RDI. That's quite nice and easy to read. Okay, I'm happy with that. Now we're looking at assignment. This here is again the same kind of stuff. And the idea is basically that we're putting something into racks. And this here, so the left-hand side in an assignment is an identifier. So I think we're probably going to do something like this, you know, and I think we can just like rip all of this out, rip all of it out. And then it's basically, we've got generate expression with the right-hand side node. And then here it's just a generate term. The left-hand side can only be a term. So that doesn't need the file. Like that. So we're moving from the result of the generate expression to the generate term. Okay. Well, these functions are getting a hell of a lot simpler now. All that complexity is down here in the generate term. The function that I was like not even knowing whether I would even need previously. This we'll deal with later. That needs some cleanup. But here I feel like this is all the same code again that we don't need. Oh, this we do need, right? Duplicate identifier. Did we rip out some code that we do actually need here? Yes, this code here I think we need. This is a check, right? Undeclared identifier, the left-hand side. Yeah, we didn't check that because this is No, it's a generate term. But an assignment, left-hand side of assignment is not a term. It's just straight up identifier. So I think we should not actually be using generate term here. Yeah. So let's bring back this. Var offset, and we'll bring back this as well. Yeah. So it was just this right-hand side stuff that we, we removed. This was all right-hand side logic, wasn't it? Yeah, that we removed and we replaced it with a generate expression. Okay, great. And down here, up here, we want to do the same thing. This is all right-hand side logic, which was putting it in racks. Oh, maybe we copied this one because it already has right-hand side in it. So instead of doing that, we want to do this. We need an F line and a %s. Great. Looking good. I think that was it, Expression is in the declaration, assignment, and exit. And I think we've handled those. Declaration is handled, assignment is handled, and exit is handled. Okay. So what happens when we generate this assembly? Index is out of range. Okay, generate expression. Because I'm assuming that there's children. I'm assuming that there's children. So I think maybe up above here. Oh, and also I'm doing this statement here, even if this happens, which means that this statement is pointless. So I think actually I need to I think basically if there's no children, that means we have a term. Right? If there's no children, let's just do the term. And down here, maybe we'll give an error. It's like an invalid node. Failed to generate expression, invalid node. Yeah, that's better. So if we come across a term when we're doing our expression, we just do that, and then we're not trying to get the children which don't exist. Okay, exit code 0. Fantastic. I think we're doing all right for time. So we declare a variable of 57, put it on the stack, advance the stack pointer. Now we're assigning the value of this variable to a new variable, so we take the value of the old variable and put it on top of the stack, then move the stack pointer. And now we do an assignment of an integer literal to an existing variable. Now we open our scope. I think I'm going to make a little tweak here. Where's our generate scope? I think I'm going to put these comments not indented. Yeah, I think I like that. It's a bit more clearer where it starts and ends. So we go into our thing and then we assign to an existing variable, which just moves the number in. We declare a new variable, so we put 10 on the stack and move the stack pointer. Then we move the stack pointer back because it's the end of the scope. And after that, we do our declare, which is using an existing variable to assign. And we'll move the stack pointer. And this is the interesting one. We do a declare. So, oh, this is the first time we've gotten an older variable. It's like 2 variables back. Is that right? It's y. So there's y, z, and then this. Y, z, and then result. So yeah, there's 2 variables back. That makes sense. Cool. So we put that in RBX. Then we add RBX, okay, to y again. That part's wrong. Y is on the left-hand side, that's true, but this should be an integer literal. And then we assign the result to the stack pointer, move the stack pointer. That looks right. And then we exit using the variable we just declared here. So I think everything looks right except for this. Add right-hand side. So let's go to our exit statement. And we generate an expression from the parameter. I think it's actually in generate expression. We're using left-hand side when we should be using right-hand side. Yeah, this should be right-hand side. These are all right-hand side. Because first we're putting the left-hand side into RBX, then we're adding the right-hand side to it. So that should be right-hand side. Yeah. Let's run that. Yeah, now we see it's 3. Awesome. Which is that what I put? Yeah, y plus 3. Okay. So if y at this point is 77 and we're adding 3, the result should be 80, right? Let's run that. Oh boy. Oh boy. We got quite a few errors there. So first, let's go to the first one. Line 4, operation size not specified. So we're moving a number onto the stack, but we're not specifying a size. Is that not how we did it before? I thought previously the code was based, oh no, previously I think we put it in a register first. And then we moved the register onto the stack. Now we're doing it directly. And I guess when we move the register onto the stack, the assembler knows the size of that register, so it knows how much to move onto the stack. Whereas here, it does not know. So we need to tell it. So this is when we're declaring and we're assigning a value. So let's go to declaration, assigning a value that's here. So I believe we want to put QWord here. Quad word is 8 bytes. So that's, and because the only type we have is a 64-bit integer. So that's 8 bytes, which is a quad word, QWord. I don't think that's going to fix all of our errors, but hopefully it should fix at least the first one. And it does. Okay. Now I think basically anywhere where we're using generate expression, we're going to have this issue. Well, that's moving into a register, so I think that's not an issue. This one is an issue because we're moving to somewhere on the stack. So maybe that's it actually. What about here? We're moving into registers, so I think that's not a problem. Okay, let's try that. Okay, that did remove another one, but here is not happy. Maybe you're not allowed to use QWord if you're doing it like that. What if I try to build that? I don't know if it's like, I've tried this before and it's failed, so I don't know if it's something to do with like not being allowed to like assign from an offset of RSP to RSP. Or do I need to like keyword both of them? Is that a thing? No, that's not a thing. Oh, did I build? I think I built and squashed it. But it's not a thing. So that just straight up doesn't work. So maybe we do need to introduce like an intermediary for now, just as a quick fix. So in here, maybe we need to do that and then just return early, but also with RBX. So then we've assign term, I don't know. So now we're putting it, we've got an intermediary. If I run that, yeah. So now we're moving it into RBX, and then we're moving RBX into here, which does not need the keyword, I don't think, because we know how big RBX is. But I think it's not a bad thing. Actually, maybe we don't need the keyword anymore at all, because we're never coming from an integer literal or anything. So maybe we can just, I'm not sure if this is true, but maybe we can just take these keywords back off. Since we're going via a 64-bit register, and the assembler might know. Yeah, now the assembler knows. Which it is, link's fine, executes fine, and we get 80. That's what we were expecting. Awesome. Okay, so let's just try our other operators. 77 minus 3 should be 74. 74. 77 times 3, I'm going to have to get a calculator out, is 231, which should be just within range of exit codes. Exit codes only got to 255, I think, but that's perfect. 231, just like we calculated. 77 divided by 7, we'll say that should give us a nice round number. 77 divided by 7 should be like 11, right? Huh. Did I just leave no, it's idiv. I think we're going to have to look. I did look earlier at this. Maybe we can find the page I looked at before. Idiv example. How does idiv work? No, I think I found a good Stack Overflow. Um, 64-bit, or maybe it's this one. Yeah, here we go. This was a good explanation. You're actually dividing a 128-bit number in RDX, RAX by RCX. So we're actually putting a really big number into these two registers. So it's like spread across two registers. And the number we're dividing by needs to be an RCX. And what was the example code? Because he did IDiv RCX. And so the result that we're looking for will be in racks. Because I think this is like the high part of the number and this is the low part of the number. So RDX we can just set to 0. He set RCX to 0. But he was confused because he was getting it wrong, right? And I think it's because he never does anything with RDX. So I think we need to set RDX to 0 so that we don't get any craziness. Put our value in racks, divide by RCX, and then the result should be in, is the result in racks. Put dividend in RDX RAX. For you, that probably means clearing out RDX and putting the dividend in RAX. Put divisor in some other register. You chose RCX, that should be fine. Then divide, result will be in RAX. So the result is always in RAX. So this operation uses RAX, which is what I was trying to avoid before because of this. But it looks like we can't avoid that. But I think we can just flip these around. So this here is going to play with RAX. It can do whatever it wants, and then in the end, we set RAX to what we want it to be. So maybe we can just RAX is where we input our left-hand side. So let's just always put the left-hand side into racks. Assign left-hand side to racks. Cool. And then the IDiv is the different one, right? This is where we're going to need to do a couple of lines, I think. So we've got the right value in RAX. Our DX needs to be cleared out. So I know XOR is supposed to be faster, but I just want to use something that's nice and clear. So I'm going to explicitly say move 0. Is there somewhere else where I say, oh, clear scope stack. Just 0 out racks or RDX. And then what we divide by, does it have to be in a register? That's what I'm interested in. So this generate term is going to give us like a number, or it's going to give us a stack address, and I don't know if IDiv is going to accept that. But let's see what happens. It's like divide by RHS. So if we run that, so here is our, where is our divide? Here it is. So we're moving a value into racks, then we clear out RDX, then we divide by 7. Divide by 7, yep. divide by 7, and then we move the result, RBX, no, not RBX. The result is in racks now. Then we move racks to the stop pointer and advance the stack pointer. So let's see if that works. I'm not sure if this putting just a 7 here is going to work. Invalid combination. It's 31. Yeah, I think it wants it to be in a register. So what's another register we can use? We're using racks and radix. So what about Rubix? I guess actually we want to like go move Rubix. And then it's just, yeah. Assign right hand side to Rubix. So we've got the left hand side in racks, clear out the higher part of the number, right hand side in Rubix, and so then we divide by Rubix. Okay. Oops. We need to run the program first. 11. 77 divided by 7, is it? What did I say? It's 11. I think there is also another register, you know, because we got the answer out of racks, which is also where we put the input, right? But we also put some input into radix, and I think after the division that holds the remainder. But we don't care about the remainder right now. We're just doing integer division. So I'm super happy with that. That's all of them working. Just to tempt fate. Just to tempt fate. I want to put that directly in there, or just to test out maybe, I don't know, like something a little different. 57 times 2, which should be 114. So if we put it directly in there, is it going to work? Because remember we had the issue with racks going all over the place. What did I say? Yeah, 114. Okay, cool. And the assembly is like, see, this is where it's doing the multiplication. It's more with division, isn't it? Actually, division is where the issue could arise. So we'll say divided by 2. 57 divided by 2 should be 28, I think. 28.5, but 28 because we just do an integer division. 28, nice. And the assembly. So yeah, this is where we put something into racks, and we set radix and Rubix, and then we do our division, and then we move the result of the division into RDI, because that's where we put the exit code for our syscall, and then we do racks 60 afterwards to avoid conflicts with this, since we're messing with racks in here. To avoid the conflict, we do this after. Perfect. Okay. That's it. We can actually do maths, at least basic maths. I'm happy with that. Okay. I think I'm pretty tempted in the next one to implement an algorithm that will handle, you know, something like +2 times 3, you know, like something where we can do that. That's what I think maybe that's what we'll do next time. But for now, thanks for stopping by. Don't forget to like if you want me to continue the series. I hope the audio was better. And yeah, if you have any suggestions or something, please leave a comment. All right. Thanks. Ciao.